Howdy y'alls. We're back again. Diabolic vTutor. We're just here to do some more graphing regarding polynomials. So let's just get started with that. So we've gone over the end behaviors. We've gone over finding the x-intercepts, and then using those in tandem to generate the graph of the function. So we're just going to do some practice problems, of course. Here's a nice graph already. Let's just do a little bit of a warm-up for these ones. So suppose we have a function. Function is going to be f of x. Good old f of x. So f of x is equal to, and then this is going to be in fully factored form already. So let's suppose we have x here, and then we have x plus 3, and then x minus 3. And let's suppose that's all we have. Well, we have something like this. If we were to graph this, let me graph this in... Yeah, let's do purple. Let's do purple. No, I'm sorry, I do different colors. Alright, so basically, again, when graphing these polynomials, all you need to do is have fully factored form, which we already do. And then determine the end behaviors, and then we should be good to go. So let us first find the end behaviors. So when we're doing the partial distribution, we have x term here. Inside factor number 1, we have factor number 2 with greatest degree term is x power 1. Right here is also the greatest degree is x power 1. So all you need to do is do partial distribution to figure out the leading coefficient, the leading term with the leading coefficient, of course. It's just coefficient 1 times 1 times 1. So we still have 1, but then we have 3 x's multiplied together with exponent 1, so it's x cubed. So this one follows the typical trajectory of the down-up motion for odd-powered exponents. So that's nice. And no signage in front aside from there's invisible positive 1 term, so no flipping shenanigans. So let's get started with the x-intercepts. So first we have x-intercept at 0. And we have an x-intercept at x is equal to -3, so -3, 0. Right there. And then lastly, we have x-intercept at positive 3. So let's get to graphing now. So again, we have this kind of downwards, upwards motion, because when you cube a very large negative number, it's still negative. Hence this downwards trend on the left hand side. Again, you could represent that using if you're writing that as a kind of a written statement as x approaches negative infinity, then you have your y values also approach negative infinity. So that is the end behavior for the left hand side. For the right hand side, it should be as x approaches positive infinity, then y approaches positive infinity. Because again, if you cube a very large size positive number, it's still going to be positive, but it will be even larger in terms of its size. So up like that. All we need to do now is to draw a nice picture that connects all those things nicely together. There's going to be some sort of turnaround, but again, I'm just going to cut it off right there. And then just technically turn around, goes back here, and goes right through. There's a turnaround. Oh my goodness. Okay. There we go. I don't like the circle-y thing. Well, let me get rid of that. Oh, that's bad. Wait a minute. Wait a minute. Oh, I'm not drawing on... Oh, I thought I was drawing on a layer. Whoops. Okay, well... Everything I said is still correct up to that point. Oh, yeah. Well, you know what? Let me just finish it. That's unfortunate. I was not aware of the layer I was on. Whoops. So again, it's just gonna look like this. It's gonna be a swoop around, and then that's gonna be the graph of f of x. All right. So that's it for the first sample problem. Let me undo all this nonsense. Is that the farthest I can go? Uh-oh. Well. You know what? Let me close this program so I don't save changes. Whoops. I'll be right back. Okay, and we're back. Whoops. And we're back. Yes. We are now on a different layer, so if I draw this and I hit delete, it's all gone. Okay, good stuff. So moving on to the next problem, we're going to have like something like a g of x. Let's actually have something that needs a little bit of work. So we're going to call this one, or this is just going to be x cubed plus 6x squared minus 40x. So we are tasked with graphing this particular function. We are given the function in standard forms, so subsequently we must fully factor it to figure out a few things. But first things first, we do have a cubic situation right here. So it's a positive x cubed, so which means that we can figure out the end behaviors for this particular function. It's going to be the same as before. It's going to be the down-up situation. So there's some sort of down edge and an up edge for the x cubed. Yes. All right, but we got to do the fully factored form first. So term number 1, 2, and 3, we notice that each term has a x factor. So therefore, please slap on the old parentheses and factor out the x. Thus unveiling this quadratic right here. It's probably a standard quadratic. Whether the factors of 40, if I could summate to be 6. Let's see, 4 and 10. Yep, there you go. That's fairly straightforward. So fully factored form is x, the larger of the two magnitudes, is positive. So plus 10 times x minus 4. Fully factored form for g of x. And of course we have the multiple zeros. We have 0 number 1, which is x is equal to negative 10, which goes, unfortunately, it goes off the scale. Wonderful. So let me modify these points real quick. So let's do increments of 2 rather than 1. Otherwise we can't fit the graph. So we're going to call this negative 10, and this is going to be positive 10. There you go. So we have our first 0 at negative 10 planted right there. Next we have x 0 at 0, so that's the other one. And then we have third 0, x is equal to positive 4, 2, 4, yes. Alright, so we're pretty much done with that one. Now we just need to make these agree with the end behaviors. Again, end behavior is cubic, so it's going to be like that. Up-down motion. So it goes downwards first, cross the x-axis. There's some sort of turnaround, turn back down, cross this x-intercept. There's some sort of turnaround, go back up, cross this x-intercept. End behavior follows cubic, positive, standard cubic. Now that we're done with this particular problem, that's nice. Okay. Next up we have, let's go back to f of x real quick. F of x, and then it's going to be x cubed plus 3x squared minus 9x minus 27. Alright. This one is a little more difficult than the previous one because not all 4 terms have x factor. Oh, but we can factor by grouping, right? So we can see that the first pair here has some similarities. This coefficient is 1. 1 times 3 is 3. This one is negative 9. Negative 9 times 3 is 27. So we can factor by grouping. Therefore, let us group those two together first, parentheticals, and then we will group those two. Alright. And from the first two terms that we've grouped together, they have x squared in common, so let's factor out x squared from those two. Very good. Divide by x squared is just x power 1. Divide by x squared is just positive 3. Nice. And then from those two in common, we have a negative sign and a negative sign, so we could factor out negative 3 from the both of those. So divide by negative 3 is positive 3x. Oh, I'm sorry, we could go a little farther. More than 3. We could divide by negative 9 from those two terms, thereby bringing negative 9 here. So we have a remainder of x inside the parenthetical, and then this one divided by negative 9 is positive 3. So that looks nice. We can slap on the old brackets and then factor out from term number 1 x minus 3, and from term number 2 also x minus 3. I mean plus 3. What am I saying? So that's currently what f of x is looking like. Take a quick survey. This is x plus 3. This is fully factored. This is a difference of 2 squares. A familiar face. So therefore, we need to factor that one as well. Difference of 2 squares, just follow your standard algorithm. What's the square root of that? X. What's the square root of just the 9? It's 3. So copy paste this one. X and 3, and then alternate with plus minus. Standard algorithm. Alright. So since this factor is the same as this factor, we could consolidate those two using exponential rules. Alright, so how many unique factors do we have? We have unique factor number 1, which is just x is equal to negative 3, but this factor has a multiplicity of 2, which I hope you remember what that does. And then we have factor number 2, the 0 for that one is x is equal to 3. It's just multiplicity 1. Alright, we already have determined the end behavior for this function. It's just going to be standard down-up situation for positive cubic. Alright, so let us plant 0 number 1 and negative 3. And then 0 number 2, positive 3. So again, this is the wrong way to do things. This is wrong. What is this nonsense, right? So we have a multiplicity of 2 on this particular factor, which means that this is a repeated 0. So when you have a repeated 0, you pay attention to even and oddness. This is an even exponent. So this factor here exhibits a parabola-like motif. So it's going to look something like this. How do I know it's going to be pointing downwards like that versus pointing upwards like this one? It's because end behavior must agree with the motif here. So we already figured out that the motif must be, as x approaches negative infinity, y approaches also negative infinity. So it has to be going downwards. And again, because this is even a powered exponent, it exhibits parabola behavior right here. So it's the touch and go rather than the strike through. So downwards trend, touch and go right here. Alright. And then since this one is just a multiplicity of 1, so odd power exponent, it just pierces right through like this. And make it agree with the end behavior we've already determined. As x approaches positive infinity, y approaches positive infinity as well. And again, there's some sort of loop around, but I just omitted that from the graph. Cut off. This is just the viewing window. Alright. So we start off with this thing right here. You can jump straight to synthetic division if you wish, or, you know, if you want to have a slightly easier time, factor by grouping. And then you realize that you have a different two squares, factor even more, fully factored form. Consolidate your same factors. Repeated factors with even multiplicities are going to be parabola-like motifs. Exponent 1 just pierce through like a linear function. Alright. That's it for that one. Moving on, of course, we have some more wacky functions. And by wacky, I mean tedious. So we have x power 5. Wonderful. And then we have plus 12x power 4 plus 9x cubed minus 270x squared and minus 324. And lastly, plus 1944. So you hope that your teacher doesn't give you something that's absurd, especially during like a time test. Otherwise, it's very annoying trying to come up with the fully factored form for this nonsense. But, you know, this is not a time test, so we're good. Okay. So what are the, what can we do to factorize this thing? Can we factor by grouping? So if we look at this particular group and then we look at this particular group, it doesn't look good because of the signages. You see how this is a positive, positive, positive? So if we group that, we cannot make that group agree with negative, negative, positive. So that's a very telltale sign that this is going to lead to kind of a sad situation. So unfortunately, I don't think we can do any sort of good factoring by grouping. So I think we're going to have to resort to just synthetic division. So in other words, we need to find candidates of 1944 and candidates of 1. That's really easy. This one is kind of a doozy. So let us first break down the 1944. So 1944, what do we have? What do we have? 2. I guess 2 is the easiest one to start off with, right? So it's going to be 9. 72, yes. It's again divisible. Can we put 4 in here? Yes, we can put 4. So let's divide by 4. So we're going to get 24, 3. This is divisible by 3. Because if you summate the digits, you get something divisible by 3. So therefore, this whole thing is divisible by 3. So divide by 3 is 81. Oh, yeah, good stuff. So that's just 9 times 9. So therefore, we have fully factored form is 2 cubed times 3 to the power of 5. Fully factored into prime factors for 1944. So we can generate all the candidates for the 0 tests. Alright, so let's see. So the first one is 1. Should I list out? Yeah, let's list it out. So 1944. And then the second one is 2. Try to recycle your work if you can. Next up is 3. 3 times what? Ooh, that's annoying. So let's divide this thing by 3. You know what? I'm going to omit the larger numbers just for sake of to expedite the process. So typically, the extreme numbers aren't going to work, especially for a pre-written problem like this one. So, you know, you're going to see me do a shortcut because I don't want to bother making too many factors. So we have 1, 2, 3. Just understand that this one corresponds to the 1944, which I'm not going to write anymore. And then this one corresponds to the 972. This one corresponds to whatever. I'm too lazy to write it out, so let me just put this placeholder. And then we have a 4 here. And do we have a 5? No. Do we have a 6? Yes, we have a 6. 8. And 12? I think is the next one. 12. Well, we're missing a 9. Yes, 9 and then 12. Etc, etc. So let's just try these ones first. Because again, the coefficient is just 1. So it's going to be fairly straightforward. I'm just going to omit these later ones. Because they're almost always wrong. Or they're not going to work. For pre-written problems like these. Alright. So let's test out. Let's check Descartes' rule of sign. So we have plus, plus, sign change number 1, sign change number 2. So there could be 2 there could be up to 2 positive real solutions, or there could be 0 positive real solutions. In terms of negative solutions, let's just check that. Oh, we're guaranteed a negative solution, since we're not necessarily guaranteed a positive solution, because this is an odd degree, and when you have odd degrees, you're guaranteed to strike through your x-axis at least once, by virtue of this one having a down-up style of end behavior. If you have down here and you have up here, you have to cross the x-axis to make them meet up. And again, since Descartes rule doesn't guarantee positive, we're probably guaranteed a negative. But let's just check real quick. So if we plug in a negative value, this is going to be negative, this is going to be positive, this is going to be negative, this is going to be negative, this is going to be positive. So how many sign changes is that? 1, 2, 3. Yeah. So we're guaranteed 1 negative real solution. So let us begin our hunt in that particular fashion. We're going to check it out with -1 first. You know, standard pick. Make sure you extract all the coefficients. So we have 5, 4, 3, 2, 1, 0. Coefficient 1. Coefficient 12. Coefficient 9. -270, -324, and then positive 1944. Alright, so let's see. This -1 probably isn't correct because I don't think it snowballs enough. So let's drop the 1. Multiplication, summation, multiplication, summation, multiplication, summate, multiply. Okay, so it's definitely not going to be enough as we've already anticipated, right? Wait, what is this? -56 is positive 56, so we end up with a positive 2000. What is this indicative of? It means that this number, we need to pick something else. So -1 resulted in a positive term. So let us keep track of that. Okay. Unfortunately, I cannot hit undo that many times, so let me manually delete this and delete this. So we know that picking a -1 resulted, a -1 as a 0 candidate resulted in a positive remainder, so, which means it's like here-ish. So we're above the x-axis. So we need to pick something that is a little bit past. Well, actually, we don't know. Is it going to be like this or like this, right? Okay, well, we need to just pick another 0. So let's pick -3. Something a little more extreme, so that way we have like a goalpost to work with. So if -3 as a 0 ends up giving a negative value, then we know that the 0 is going to be at 2 if it's a nice 0. Alright, let's check it out. So drop the 1, multiply, sum, multiply, sum, multiply, what is that? 48? No, is it? What is it? 56. What am I saying? This is 9 times 6, which is 56. 54. Yikes. Alright, summate that. So we have -216, yes. Multiply that. What is that? Oh, that looks kind of annoying. Let me think. Yeah. Multiply by 3. We're going to get that one. Negative. No, positive. Because negative times negative is positive. Summate those ones. We're going to get... And then lastly, multiply those two. So unfortunately, not quite there because we got we get a positive result as well. So we need to go a little farther. So that's unfortunate. And that's now to manually delete this. Okay, so we tested out the -3 that also resulted in a positive remainder. So just to anchor where we're currently at, we're just trying to factorize the polynomial. And then when it's a weird polynomial, when it's an exceedingly long polynomial with like a lot of factors, it's very annoying. So again, we saw that the -3 resulted in some positive solution, positive remainder. So let's try 6. -6, I mean. -6. So drop that. Product, sum, product, sum. What is that, 27? Yes. Product. I'm really worried that maybe for the previous one I did it wrong. Right, that's always a nagging issue. Potentially nagging issue. So we have 6 is 42. Yes, and then we carry 4, 12. Yeah, this should be correct. This should be positive. So be very careful with the plus minus situations. 8. I think that's correct. Yeah. And then multiplication again. We're going to get the negative answer. So 8 times 6 is 40. I need to write this down. I think that's right. Subbing those two, we're going to get the 324, and then multiplying that. Ooh, I think this might be good. It might be good. 6 times 4 is 24. Carry the 2, 12, 4, perfect. Yeah, it looks good. 1 plus 19, yes. With a negative times positive, gets us negative indeed. Alright, perfect. This is a success. So, therefore, this must be a 0 of the function. Therefore, x plus 6 must be a factor of h of x. Cool. And again, don't forget what this thing here means. It means that those ones are your quotient. So we have x power 5, and the rest of these divided by x power 1, so this should be x power 4. X power 3, x power 2, x power 1. So I'm just going to copy paste that. With the plus sign, of course. And I'll just delete this part. And because this is still degree 4, we continue on, we trudge along with the factorization process still. Again, we already determined that -1 doesn't work out and -3 doesn't work out. So we still have positive answers to potentially check out. So let us check positive 2, but let us extract the coefficients. Well, again, this is 4, 3, 2, 1, 0. Because the synthetic division is very mechanical. You need all players present. Otherwise, it just breaks down. It gives you bad results. So let us test the positive 2 and just see what happens for that one. So you have 1, 2, 8, 16, -11, -22, and what is that? 686. Yeah. Multiplying that one. Okay, so that gives us a positive result. So not tremendously useful for 2. What went wrong? Let me think. So this number is positive. We need it to be negative. In order for this one to be negative, this one needs to be larger. Yeah, in order for this one to be larger, this one has to be larger. Then this one needs to be negative. Okay. That's a little hard to gauge. So 2 also leads to a positive situation. Let us try something larger like 8. Let me see what happens. So drop that, sum 8, multiply sum 8, and then 14, multiply. No, we're going to get a positive number in the end. So going with a larger number, any 0 candidates larger than 6 will give us a positive result, because this one times 14 is going to give us 111, and then you're going to get a positive result, and then it just snowballs from there. You're going to get more positive, positive, and positive. So anything after 8 is not a good candidate. We already tried 2. We could try 1, I guess. Alright. So let's try 1 to see what happens. I don't think it's going to be large enough, though. I think we have to stick with our negative. Yep. This is too small. So you multiply that one. Negative 20. But once you get to here, it's all positive. So we don't have any positive real solutions. So let us get rid of those. So we still have negative candidates to try out, though, right? We've already tried -1. We've already tried -3. We've already tried -2. I guess we need to try -8, right? So let's try -8. Let's see what happens. Product, sum, product, sum, product, sum. Oh, that's too large. You see that? That is too large. We're going to get 196, and when you multiply that, that's too large of a negative. Too large now. Which means the final result is going to be negative. Yeah. Okay, so that's informative. So we have -8 results in a negative answer. Alright, not bad. You know what? We might have a duplicate answer on... We might have a repeated 0 at -6. So let us assume that. So I'll get -8 as a 0 candidate results in a negative remainder. Let's try this one. It's a 0. That's a 0. That's nice. Easy work. Then we have a -6 times -27. So what is that? That's 162, I think. 42 to 162. Yeah, 162. A positive 162, of course. If we summate that, yeah, that's going to be too large. This is going to be 270. So when you multiply by -6, this is going to be too large of a negative, and this will be a negative situation. All right. What does that mean for us? It means that we still have 4. We've already tried -1. And then that was like the first one. The -1 did not work. If it did not work for the first synthetic division, it's not going to work for the second synthetic division. So -1 is out the window, unless I messed up something along the way. The -3 also didn't work, and then the negative... Did we try -2? We tried +2 or -2? I don't remember. All right, let me try -2. I have a feeling that I've already tried -2, but let me try it again, just in case I missed it or I messed up the math. Because I think I might have messed it up, maybe. All right, this is gonna be -8. So sum 8 is -35. It's +70. Oh, you know what? That looks kind of good. No, it's not. It doesn't have it has a 6 ending. This needs a 4 ending, unfortunately. So this is 178, and when you multiply that, that is -356, which is very close, but it's a negative answer. So that's good, right? So the fact that that's negative is a good sign. But unfortunately, it's not what we want. Okay. So -2 got us to negative situation. And so did -8. -4 then? I also have a feeling I already tried that, but I forgot to note it down. Let's see. So, product, sum, product, sum. Yeah, this feels very familiar. And then product. What's that? 20, 140. Yes, I think. Right? 20 plus 120, 140. Yeah. Summate is 248. This is not good because 4 times 8 doesn't give us a 4 ending, unfortunately. And it's also too large, size negative. That's like negative 900 something, which is also negative. Okay, well, that has also failed. Wonderful. We love factorization problems, do we not? So, -4 unfortunately got us to that nonsense as well. It was too large, right? You know, I'm gonna try -3 again. Because I have a very faint feeling I might have botched up the mathematics somewhere. So, yeah. Let's hope it doesn't get all botched up again. Oh, that's weird. Wait a minute. What? Oh, it's positive. I'm sorry. It's positive 108. Yeah. Right? 90 plus 18, 108. Yes. And then you summate that one. That's 216. If you multiply that, that's too large because -3 times 2 gets you like -600-ish. So therefore the answer is like -200-ish. Which means it's not what we want. Wonderful. Let me think about this. Is there something I'm missing? So what have I tried so far? What's been tried so far? Well, Descartes' rule of sign is reported a few things. Let me think about this. I hope I didn't mess up the signs. I really hope I didn't mess up the signs. Let me see something. Oh, I'm going to cheat. I'm going to go to my calculator because I really hope I didn't mess something up for the sake of time. Unfortunately, you won't always have access to a calculator during your test, for example. But I'm just doing this so I don't spend too much time on this problem. Let's see. Again, there's a chance I may have botched up the copy paste. Ooh, did I mess it up? I think I did. Huh. Yeah, I think I messed something up. Something's not right. When I input this in my calculator, it doesn't come up with nice real roots. It came up with irrational roots, which probably means I messed up something. Wonderful. Okay. Well, unfortunately, we're just going to have to backtrack just a little bit. So thankfully, VOD watchers can skip. But let me test this out again. Let's clear that, and then let's clear that. Let me double check to make sure the problem is written correctly. 5 x power 5, 12x4, 9x cubed, -270x squared, yes. And then -324, +1944, yes. Let's do the synthetic division again, just to double check. Let me make sure of something. Let me copy paste this just to see if I miscopied. We'll delete all that. So let me put this as a comparison, just to make sure that I didn't screw things up too badly. So coefficient for the first term is 1, second term is 12, third term is 9, fourth coefficient is 270. Fifth coefficient is 324. And the last one's just constant, 1944. Alright, so this is the -6 is the 0 candidate. Let me test this real quick. Let me think about that. That's 2, 4. Yeah. Summate that one is 8, 108. The negative, multiplying that is 48 in the ending. And then 6. Positive, yes. And summating those ones, we get 324. Multiplying those two, we are going to get the 4 ending that we desired, and then 12 plus 2 is 14. Carry the 1, 19. This is a negative. Perfect. Okay, let's double check. Oh, this is where things went wrong. You see how this one is a negative result? I copied a positive result, which is why I kept screwing up. Okay, good. Well, now I know. Wonderful. So let us continue on with the syntactic division. That means that most of the information, the 4 is now wrong. Let's try -6 again. Yeah. Wonderful. Okay, good thing I checked the calculator just to confirm my suspicion. If I had written it correctly, if the quotient I had was correct, then the calculator would have factored it for me. But since it didn't factor correctly, since the calculator did not give me good factors, it means that what I had written was wrong. The quotient I had written was wrong. So let's try -6 again. 0, 0, 27. Then we have positive what? Oh, it's just going to be this one again. Right? 2, 4, yeah. Negative times negative is positive. Okay, good. And then when you summate those two, we are going to get 4. My brain is failing me today. Let's see. 160. Yeah, so this is correct. And then lastly, multiply those ones times that one. That looks pretty good. Oh, okay, it is good. Oh, thank goodness. So we have -300 plus -24, so -324. Yes. Thank goodness. Let's make sure the signs are correct. So that's going to be negative, yes. Positive, yes. Okay. So we have a repeated factor right there because -6 works again to produce the 0. -6 is therefore a 0. Therefore, x plus 6 is a factor. We would just consolidate it with the previous information from the first syntactic division. Okay. Now we have this thing, and this is where we can jump to our favorite. Wait, can we? No, it's still cubic, unfortunately. This is still cubic. Okay. So we can't quite jump to syntactic quadratic factoring just yet. So let us. What do we have here? Let's try -6 again. I don't know. I'm out of ideas. Summate. Product. Summate. What is that? That's a 9. No. +9. Yes. Yeah. Wait. Oh, is that +9? Yeah, it's +9. What am I saying? +9. Lastly, oh, what do you know? It worked again. Okay, good. Good. Gets us 0. Clean. So we have another x plus 6. So we don't have squared now. We now have cubes of x plus 6. There you go. Okay. This looks like a factorizable quadratic at this point. So it is x squared minus 6x plus 9. If you think about that one, right? What's half of -6? It's -3. What's -3 squared? It's +9. So this is a perfect square. So therefore, x minus 3 squared. Coupled with that one. Okay, good. So this is now fully factored form. We have three factors that are repeated. The x minus 6 is repeated 3 times. And then we have the other factor, x minus 3, which is repeated twice. So how do we, now we get to the main heart of what we were supposed to do. How do we graph this junk? Factorized h of x. So first 0 as x is equal to negative 6. Planted there. And then we have x is equal to positive 3 as our second unique 0. Planted right there. We already talked about the end behaviors. It's going to be x power 5. Well, we haven't talked about it. It's x power 5, so it's an odd-powered positive coefficient, so it goes down up like a cubic function. All right. We have repeated multiplicity of 3 on this one, so it's just going to be straight pierce through. We have a multiplicity of 2 on the x minus 3 on this particular 0, so it's going to be the touch and go right. Where did it go? Right here? Did I delete it? So it's going to be touch and go right here. And now we'll just make sure we connect these as smoothly as possible. We could do something like this, but again, I'm just going to cut it off. Just know that it loops back around somewhere. And that's the full graph. Let's double check. Odd powered exponent, so it goes down up because also with a positive coefficient, so we're good with that. We have odd powered multiplicity for right here, so it's just going to be straight strike through. And then we have even multiplicity for x0 at 3, so it's going to be touch and go. So that should be correct. Yeah. Perfect. Okay, moving on. We have much more annoying problems, of course. I'll try not to get too bogged down by the tedious mathematics. Sometimes it just can't be helped. Sometimes you get really bad polynomials. So here's another polynomial. X power 9, that's absolutely terrific. And then 12x power 7, and then plus 48 x power 5. Notice this down ticking by 2. Interesting. That should be kind of suspicious. Minus 64x. What is it? Cube? Yeah, cube. Okay, so again, there is a pattern of downcreasing by 2 per exponent. So that seems kind of weird. We have plus minus alteration, so maybe factor by grouping. So let's test that out real quick. So if we choose to factor by grouping, if we group those two, we can factor out the x power 7, thus getting x squared minus 12. That's not the best. And then if we group these two together, we can factor out what? 8? 8x cubed, I think. 8x cubed. No, we could do a little better than that. We could factor out 16. So if you factor out 16 from this term and this term, and we also factor out x cubed, what will we get? On the inside, we are going to get 4. Oh, that's bad, because it doesn't match this one already. But that's okay. We'll continue. Let's see what else we got. No, that's not 4. What am I saying? 3. 3x. Which is still not good because it's mismatched. So factor by grouping seems to be a bust at this point. And then divided by 16 is negative 4. Alright, well, that was definitely a try. But it failed. Are there any fancy factoring techniques we can possibly use? Any fancy factor by grouping that we can use? Let me think. Let me think about this. We have coefficient 1 and then negative 12. There's a possibility of splitting these two up, right? Let me think about this. And we have a 64 right there. Is it worth it? You know what? I don't think it's going to be worth it. We can potentially split this into, for example, something like a plus 12. No, 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 no. We can split into like a minus 12x power 7, and then we have also minus a x 7. And we could set up a system of equations with that one, and we could also set it up for this 48x power 5, but I think it's more trouble than it's worth. The reason why I'm saying that is because the factors of 24, there aren't that many of them, and this is just coefficient 1, so we could probably just get away with synthetic division. Yeah, let's do that instead. Okay. But there seems to be some sort of pattern, right? So that's kind of alarming. Okay, so let us jump to synthetic division, of course. Make sure all your terms are present and accounted for. We have 9. We skipped 8, 7, 6, 5, 4, 3, 2, 1. So we're missing a good number of terms. So we're missing 0x8, 0x6, 0x4, 0x2, 0x1, and then constant 0. Wait, do we need that for the constant? No. Oh, wait, we could factor out x cubed from all of these. I forgot about that. Whoops. My mistake. Lesson learned, right? So we have 4 terms, and each of these 4 terms has an x cubed in it, so let us first factor out x cubed. Oh, thank goodness. So factor out x cubed, we're getting x power 6. Factor out x cubed, we get x power 4. We're going to get x power 2. And then lastly, 64. Constant. Okay, well, that certainly looks a lot better than what it did before. Oh, slightly, I should say. Is factor by grouping at this point, is it worth it? Can we even factor by grouping? Let me think. It's still the same issue. If we try to factor out 16, it's still 3/4, as mentioned before. But again, the question is, can I somehow split these ones to make something nice? Again, I don't think it's worth it. Let's just jump straight to synthetic division. So coefficient for the 6th degree is 1. There's technically a 5th degree, 4th degree, 3rd degree is 0. 2nd degree is negative 48. And then x power 1 is technically 0. Constant is negative 64. Alright. So we're jumping to the synthetic division. What are the 0 candidates? It's going to be factors of 64 over factors of 1. So not too bad. 1, 64. Again, you don't need to list the more extreme ones typically. 2 and 32. Probably not 32. We have 4 and 16. And then we have 8. That's it. So these are the only real candidates that we probably need to check. So let's check. Because these coefficients are even, I'm not going to test 1. I'm going to test 2. But let's check Descartes' rule of sign. So we have positive to negative is 1 change. That's 2 change. That's 3 changes. So we're guaranteed 1 positive real solution. So I'm going to pick 2 as my first candidate for positive real solution. Based off of 2 things again. Based off of the Descartes' rule of signs and based off of the coefficient pattern. They're all evens. So let's check this out. Multiply, sum, product, sum, product, sum, product. Oh, that looks bad. That looks bad. We have negative 80, and then, yeah, that's bad. But I'm going to carry all the way through just to see what happens, because we can still use intermediate value theorem sometimes. So we have a negative answer in the end. So 2 is not the 0 we're looking for. So maybe I had to go back to 1 after all. Interesting. Well, I feel like 1 isn't going to work. Yeah, just by judging the numbers, it doesn't look like 1 is going to work. Huh, but we're guaranteed 1 positive number, though. That's weird. Let's pick 4. This one resulted in, what was it, negative? Yes. So let's pick 4. That's weird though. I would have expected 2 to work. Summate product sum product sum. Oh, what is that? Oh my goodness. 6 times 8, 8 times 8, 2 8s, 16. Yeah, 16. Pause at 16. That's weird. That's very tragic. Okay, so we had too big of a positive at this point, so it's going to be positive something in the end. Okay. So according to intermediate value theorem, we're supposed to have a positive 0 between 2 and 4. Interesting. That's really weird. Okay, well. Am I just really sloppy today? Let me think. Well, let me write down that data again. So positive 4 as a 0 candidate reports back a positive result in the end. Unfortunately, I'm going to double check too. I don't trust myself at this point. Yeah, it's too large. That's too large. It's too negative. Yep. Okay, so we might have irrational answers, but I guess we should try negative answers as well. Let's use Descartes' rule of sign. If this is a negative, if this is negative, this is gonna be positive. This is gonna be negative, and then that will be positive. So we have 1, 2, we have 1, 2, 3 sign changes, right? No, I should test this one out. Yeah. And that's a 1. Yeah, so we're guaranteed 1 positive real solution. And then if it's irrational, that doesn't make any sense, because if it's irrational, that means that the quadratic equation will report 2 answers that are irrational. So that's very strange. So, interesting. Is there a factor of 64 that's between 2 and 4? I don't think so. I think we've hit all the prime factors. I mean, all the factors. Yeah, because 64 just consists of a bunch of 2's, so there's no way we get like a Huh. This is very striking. Oh wait, no. Scratch what I said like 3 minutes ago. We can have 2 irrational values as zeros between 2 and 4. So that is very annoying. Okay, well, let's test 1. Let me see what 1 gives. I'm just curious. I don't think 1's going to work though. But I just have to see. Yeah, doesn't work. Gets us a negative value. Alright, let me double check to make sure I've written the problem correctly again. We have x power 9, we have negative 12x5, we have positive 48x5, negative 64x cubed. Okay. And we factored out the cubic from each of those terms, so this is correct. 3 plus 4 is 7, and then 3 plus 2 is 5, 3 plus 0 is 3, yes. Now making sure the coefficients are present, this is 1, exponent 5 is 0, this is negative 12, exponent 3 is 0, this coefficient here, exponent 1 is 0, yes, and then negative 64 is negative 64, okay. Well, I guess we gotta try negative values at this point. Let's try -4. I thought that the positive real solution would have been good, but yeah, let's try -2. I don't think -4 is gonna work. Summation. Product. Summation. Product. Sum. Product. Uh-oh. Let me double check the signs. I'm just slipping up everything today. Yes. Okay, that's bad. That's very unfortunate. Yeah, I think the 4 would have been probably worse. So big negative answer in the end. That's also a tragedy. That is weird. I don't think -1 is going to work because at some point we're going to add 1 to here and we get like an 11. Can it? It will never change back to even, so we'll always have a remainder. So that's not going to work. So what gives? I'm out of ideas at this point. Sum. Product. I don't think this is going to work either. Huh. 64 minus 48. That's 6 times 8, 8 times 8. This feels familiar. 2 times 4 is 6. We have 16. Positive. Yeah, it's just this awkward spacing. Okay, so the -4 gets us back to a negative remainder, right? Okay. Huh. Let me think about this again. What do we have here? Is this even factorizable at this point? Well, we have, again, according to Descartes' rule of sign, this is positive changing to negative. That's one sign change. So we're guaranteed one positive real solution. But it eludes us at the moment. Yep. 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 I don't think pushing for a larger positive value is going to work either. So if you put 8, for example, you see how it's already exceedingly large. So what recourse do we have? Let me think. So this one got us back to, what did it get us? It's a negative or positive. I should have written down that information, right? I think it got us a negative out, yes. Huh. I'm gonna check something real quick. I have no choice but to go back to the calculator. Just to double check that this problem is written correctly. Now let's see. Huh. According to the calculator, the real roots are irrational. Weird. Okay, there's a chance that I may have written this problem incorrectly. Let me see if I can find my work. How did I generate this problem, right? Okay. Let me type this up again for its full form. Why are these problems so scuffed today? Minus 64x cubed. Alright, let's see. Do we have factorize? Ooh, what? It does factorize. Interesting. Huh. Okay, so here's what I'm saying. I'm saying that the factorization for the first factorization of the x cubed is correct, right? And then we're supposed to have positive 2 and negative 2 is supposed to work as answers, which means something is weird. Something's amiss. Hold on. Okay. So just double checking my work. So you see how this one right here, there's a negative here, which means I did it wrong? Okay. Let's start over. Let me start over again, just to get it back to be fresh. Okay. Well, this is annoying. Let's see. Let me write down the full thing. Plus 0x power 5, and then minus 12x power 4, plus 0x power 3. So this is where VOD watchers will start. Minus 48x squared plus 0x minus 64. So I'm going to be very, very careful. 1, coefficient 0, negative 12, 0, negative 48, 0, and then negative 64. Could have sworn I already did 2. So 2 as a 0, according to the calculator, should work out. So no goof ups. I'll try to do no goof ups. This is a 4. This is a negative 8. This is a negative 16. The sum is negative 16. That sum is negative 32. That sum is negative 80. Huh, see? So what is wrong? Huh. That's weird. I'm actually out of ideas for this. Why is it screwing up like this? Let me think. Let me think. I'm going to move this down for a few moments. Let me try something else. Let me try an alternative strat, which is basically a variation of remainder factor theorem, where we just plug it in directly. We plug in our 0 candidate directly, and if we get 0, then it should be a factor. So let's jump to here. Let's just look inside here. I'm going to try the 0 candidate is positive 2. So we're going to plug in positive 2 into here, 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 and work out the mathematics. So we're going to get 2 to the power of 6 minus 12 times 2 to the power of 4. Because again, we're plugging in the 2. And then minus 48 times 2 to the power of 2 minus 64. Let's see what that gets us. So this is, what is that? That's 4 to the power of 3, which is 64. This one is what? 2 times 2 is 4, 16. 16 times 12. That's kind of bad. 16 times 12. It's 160 plus 32. 192. And then this one is, what is that? That's going to be 4 times that one, which is 2, 3, 192. Okay, that's kind of not looking good. And then minus 64. Okay, so that ends up being wrong too. Interesting. But, you know, I should double check my math. Maybe my math is just really bad today. 2 to the power of 6 is 64, yes. 12 times 2 to the power of 4 is 192, yes, that is correct. And then... oh, I see what I did. Okay, I see what I did. And it's such a dumb thing that I did. You see how this is positive 48? I wrote down negative 48. How did this happen? Again, with the previous problem. So this is supposed to be plus, and this is supposed to be plus, which explains why this one is not canceling. It's supposed to be plus. Those two will cancel, and then those two would cancel. Okay. Which means we can start over yet again. I need to be very careful in how I copy these problems. Okay, now that it's happened twice, and I guess this is some sort of advice when you're doing these type of problems. There are some things, sometimes people mess up during math class and they say, oh, it's because of careless mistake. But this careless mistake seems to be consistent for today at least, where I'm miscopying the signages. So this is like a plus, I copied it to a minus, which propagates, and then everything ends up being wrong in the end. Okay, so, oh, mystery solved. I should have figured it out when I plugged in the calculator. I plugged in the original one and it worked, but I plugged in my factored one and it didn't work. So that must mean I miscopied something. Okay. Alright, so let's just start afresh for the VOD user. So nothing is... we're just going to skip everything else. Just pretend the past 20 minutes or so never happened. Alright, so this is going to be we are starting now. This is our polynomial k of x. We notice that we have 4 terms. We can factor out x cubed from each of those because it's common to all 4 terms. So, minus 3 is 6. Minus 3 is 4. Minus 3 is 2. We'll copy this down correctly. So we have x power 2, and then of course this is just plain old 64. Perfect. Let's jump to synthetic division, but remember we do have invisible terms. We have 0x power 5, we have 0x power 3, we have x power 2, we are missing x power 1. So that accounts for all terms, and now we can plant that into our synthetic division algorithm. So coefficient 1, 0, negative 12, 0, positive 48, 0, and then negative 64. Perfect. Okay, and of course we tried the synthetic division, but first, what are our candidates? Our candidates are factors of 64, so I'm going to list on the easiest few factors first. 1 and 64, but I'm not going to write 64. 2 and 32, I'm not going to write 32. 4 and 16, I guess I'll write 16. And then we have no 6s, 8s, and that's it. So these are the only real candidates we need to consider. According to Descartes' rule of sign, we have a positive sign change. That's a 1 change, 2 change, 3 change. So we're guaranteed one positive real solution. There you go. We're going to try the 2 because of look how these coefficients are all even. So big clue, it's going to be 2 or 4. Well, let's try the smaller of the 2. So our 0 candidate is 2. Let's chomp through the mathematics. Summate, product, sum, product, sum, product, sum. So we're going to multiply by 2 twice, so we will get the 64 right here, so that's looking good. So 2 times 16, summate, and then multiply. Perfect. It worked out. What do you know? Anyway, that's wonderful. So we have this one. This works as a 0 because it got us 0 remainder. Therefore, our factor, at least one of them, is x minus 2. So we were guaranteed one positive real solution. We have up to 3 positive real solutions. So you see all these coefficients are all even. That's a very, very big suspicion that 2 might work again. Let's try positive 2 again. Let's just see. So we have 2, we have 4, we have 8, we have 0, that's nice. We have 0, negative 16, that's nice. Negative 32, which gives us negative 16. Perfect. Multiply. That's negative 32, which, what do you know? That's nice. So we have this solution repeated twice. So it's squared. Why not run 2 one more time, right? Because these coefficients are very suspicious. So drop down the 1, multiply, summate, multiply, summate, multiply. Wait, why is it 24? Okay, whatever. Try it out. Whoops, 24. We'll try it out anyway. That's going to be positive 8. Oh, thank goodness. And we have positive 16. Summation is 0. That's good. So we actually have this one repeated 3 times. Okay. Okay. So we have, what do we have at this point? This is still a cubic function, and the coefficients, this is a positive, this is positive, this is positive, this is positive. So we're not going to try positive 2 one more time because all these things are positive. So we need a negative answer at this point. We've captured 3 real positive solutions. So according to Descartes' rule of sign, we should have no more positive real solutions. So let's start with the negative. Negative 2, why not? So summate, product, sum, product, sum, and then product. There you go. That's nice. Which means this is a 0 since it got us a remainder of 0, which means x plus 2 is a factor. What is this though? That's a quadratic at this point because we start off with x power 6. We did this many synthetic divisions, so we removed exponent 4, so 6 minus 4 is 2, which means this one is technically x power 2. This is x power 1, x power 0. So this one is a quadratic. You could use your favorite factoring algorithm for that one, but you can recognize that half of this squared is that one. So this is a perfect square trinomial. That's going to be x plus 2 squared. Finally, let us combine all our answers together. So we have this one here, and then we have those two, which combine to make x plus 2 to the power of 3. Which means this is fully factored form. Fully factored form is right here for k of x. Alright, so let us begin to consider a few things. Let's consider, oh, this is not the fully factored form. Almost goofed up. And the reason why it's not fully factored form is because we all, oh, at least I almost forgot to put this one, x cubed. Don't forget to put x cubed. Because we factored it out way in the beginning. And I remembered to do that because I was going to go consider the end behaviors. And when I looked at this is x power 9. And then those ones don't multiply to become x power 9. Which tells me that there's a missing factor. And there it is. Okay. So this is fully factored form. So we have the leading term is x power 9. It's positive x power 9. So it's odd degree. It's going to behave in this particular fashion. Because again, with the positive coefficient. So therefore, let's mark down the zeros. So we have a 0 at -2. That's from that one. It's a multiplicity 3, so it's a pierce through. And then we have a 0 at 0. Also repeated 3 times. And then lastly, we have a 0 at +2. Repeated 3 times, but that's kind of irrelevant. Let's make it agree with the first thing we'd stated before with the end behaviors. So it's supposed to be going down and then up. All you need to do is connect these as smoothly as possible. So again, this goes down first. It loops back around somewhere along the way. Goes back here. Ooh, as I goofed up. Okay. Good enough. It's going to be doing something like this, of course. Again, somewhere along the way, loops back up. And that's it. You should probably put these little humps there. I don't like the way they look, but that's what it's going to look like for the graph of k of x, and then we are done with this particular problem. What a doozy. Okay. Let me cross those out, just to make sure I don't do those again by accident. And again, we made note that I miscopied the sign twice already. So for the next one, I'm going to be very careful with how I copy the signs. Alright. So next graph up, next function up, we have p of x. P of x is equal to x cubed minus 27. I hope you recognize this one. This is a difference of cube number 1 and then cube number 2. So use your favorite factoring algorithm. You could still use synthetic division. It's very easy. But you could also just use the algorithm if you memorized it. So what's the cubic root of that? It's x. What's the cubic root of negative 27? It's negative 3. Here's the algorithm. This one squared takes you to first term inside parenthetical. This one times this one, flip the sign, takes you to second term. And then for the third time inside this parentheses, it's this one squared takes you here. Alright. And if you recall, this one is no longer factorizable. It's x power 1. This one is never factorizable, in my experience. You can verify this using discriminant test, because 3 squared is 9. 9 minus 4 times 9 is negative inside the radical for your discriminant test, which means you have no real solutions for this one. So unfactorizable. So we only have 1 0 for p of x, and this is a cubic, and that's perfectly fine. So we have a 0 at positive 3. And behavior for this one is just our favorite cubic yet again. So it's going to be doing the down-up motif. So from here, we're going to have a down, pierce through because it's only degree 1. And because I think this one actually does do a little loop-de-loop thing. I believe so. I don't know. Something like that. And that's it for this particular function. You know what? I'm not sure if it does this loop-de-loop. Let me bust out the old calculus real quick. Hold on. So if you haven't done calculus at this point, don't worry about it. So let me just see something real quick. Okay, so we have derivative. Okay, just ignore my mumblings for now. This is p of x. Make it a 0. So we have a 0. It's only occurring at 0. What? Oh, okay. Wait. That means there's... What does this mean? That means there's an inflection point at 0. What? Right? Interesting. Okay. So -1 gets us a positive, and then +1 gets us also positive, which means it's positive, which means it's an inflection point, which means we don't have a loop-de-loop. Okay, so all that, this calculus mini thing, tangent right here, is just to tell us that there's no loop-de-loop thing. Don't worry about, if you don't have calculus at this point, don't worry about it. It's just an inflection point at 0. Interesting. Okay, so take a step back. We have a 0 at +3, and then we have the rest of our graph. It's supposed to be down up because of this one right here. It's going to be doing something like this. Our inflection point is at 0, so it's like this. Again, don't worry about how I got this. That's using calculus, which is typically after you go through this entire Algebra 1/Algebra 2/pre-calculus stuff. This is like more pre-calc, but it's also an Algebra 2. I know the title that I put is just Algebra. It's a very vague algebra, but I think most courses this is covered under pre-calc, or a bit of a Algebra 2. Okay, so that's a interesting problem. Supplemented with sneaky calculus. Alright, next problem up, we have q of x. And that is equal to x power 4 minus 1. So this one, technically, if you know your graph shifting rules, this is actually really easy, and you don't need to do fully factored form in order to figure out what this is. But we're going to do it later. I'm going to show you just how to graph this using parental shifts. So go back to your parabolas. If you recall, if you have y is equal to x squared, it's just your standard parabola. Your vertex is planted at 0, 0, and then you do the 1 to 1 movement, and then you do the 2 to 4 movement, and then you do the 3 to 9 movement. And then you just mirror everything over to the other side, exploiting the symmetry of the graph. And in order to do things, remember your shifting rules. This is -1 outside of your parental function, so it's -1, which means you have a downshift of your entire function by 1 space. It just moves down by 1 space, and that's what the graph will look like. Yes. But we don't have a parabola. We have x power 4, which is similar to a parabola. You still start at 0, 0. It's still going to be 1 to 1. But instead of being 2 to 4, it's going to be 2 to 16. So there's a very big explosion upwards. And the other thing, because this is power 4, you have a more beveled bottom. You have a more collapsed bottom portion, because if you raise fractions that have a smaller size than 1 to a +4 exponent, they get really small. So let me point that out real quick. If you start off with your generic parabola, that's going to be our base comparison. If you have exponent 4, the parts between -1 and +1 just get flatter, like this. And then if you have x power 8, for example, this part gets even flatter. So something like that. Again, it has to be between 1 and -1. That's where you're getting the flattening part. Because again, you're raising small numbers to the power of 8 or something like that. Anytime you raise fractions that are smaller than 1 and are positive, to greater and greater exponents, they become smaller and smaller. Alright. So all of that was just to say that the parental function graph first is something like this. Well, if I draw this better, let's draw it a little better. Okay. And then all we have to do is just do a downshift by one space. So there it is, and that's what the graph is going to look like if you just exploit your grafting, your basic graphing rules. Not grafting, I'm sorry. Graphing, not grafting. Like, not grafting plants. Not like Godric. So we have the graph of this one is just right there. Again, all you need to do is use basic shifting rules and then understand where to plant your x power 4 function to begin with. But let us pretend we have to fully factorize this function first. So many f's. So we have q of x is equal to x power 4 minus 1. The synthetic division is very easy, but we're not going to jump straight to that because I hope you recognize that this is a difference of square number 1 and square number 2, so we can factor it as such. So we factorize into x plus 2, x squared plus 1, I mean. And then we have x squared minus 1. And if you notice, this one is a difference of 2 squares yet again. So difference, square number 1, square number 2. So this is further factorizable. This one is a sum. This one is not factorizable. You could check using discriminant test. So this one factorizes, follow your algorithm, x minus 1 times x plus 1. There it is. So again, the two middle terms cancel out. The positive x cancels out with the negative x, thereby giving you 0x in between, which is not written here. The negative 1 times positive 1 gets you there, and then the x times x gets you there. This one fails discriminant test because the discriminant is the b term is 0, right? Because if you write it in standard form, it's x squared plus 0x plus 1. If you square the 0, it's still 0. And then you have to do minus 4 times 1 times 1. That gets you a negative 4 in the discriminant, which means this one is not factorizable if you're looking for real solutions. Alright. So I'm just going to copy paste x squared plus 1. So this is fully factored form for q of x. Wonderful. So let us plant the zeros. So we have a 0 at negative 1. And we have a 0 at positive 1. Again, this one doesn't have a 0, a real 0 at least. This is going to be x power 4. So because this is an even exponent, we know it does an up-up type style motion, as we mentioned before. So from this first 0, it's going to be going upwards. And then from the second 0, it also goes upwards to match our end behavior analysis. And then this is a little artsy. You don't need to do this one anymore. And the reason why you don't need to do it is because this one, you could plug in 0 right between them. Because that's a very easy plug and chug. If you plug in 0, 0 to the power 4 is 0. And then 0 minus 1 is negative 1. So we know to plant it exactly at negative 1. There it is. As what we mentioned before, this agrees with our shifting rule graph. So take your pick. For these problems, you usually have to do fully factored form. But this happens to be one of those few exceptions. So we are done with q of x. Alright. Let us move on to, what else did they do? We did the basic quadratic one. We've already done the factor by grouping one. Let's do another one right here. Do I want to do this one? Yeah, let's do this one. It's kind of weird though. We have h of x is equal to negative x cubed plus 12x plus 16. So So this one's pretty interesting because there are so few terms, right? There's only 3 terms, and this is x power 3. Interesting. We usually expect like 4 terms. So that's kind of a weird thing to make note of. Can we make any other observations? I think that's it. This is basically a 3rd degree polynomial. It's a negative in front, so instead of being down up like this, like typical ones, it's actually flipped because of this negative sign in front. So it is up, kind of down behavior for this one. Alright, so I guess we could just jump straight to synthetic division. That's what I'm going to default to. There's no factor by grouping that I can see. We can't factor something from all 3 terms. So I'm just going to jump straight to it. Because again, factors of 16, very easy to come across. And this is only -1. So not a lot to consider for our factoring choices. But first, make sure to populate your synthetic division. Make sure you have all terms present. 3, 2 is missing, 1, and then 0. So coefficient here is -1. There is an invisible 0x squared. There's positive 12, positive 16. So again, the candidates are very slim pickings. Factors of 16, 1, 2, 4, 8, and 16. 1 times 16, 2 times 8, 4 times 4. Alright. These numbers are very small, so I'm going to try 4 first. Not 2, not 1. Alright, let's see. Drop the... Oh, I forgot to use Descartes' rule of sign. I'm sorry. Let's use Descartes' rule of sign. There is 1 sign change, so we're guaranteed 1 positive real solution, which I'm going to stick with my positive for. So drop down the -1, multiply, summate, multiply, summate, and of course, it works out. No miscopying this time, right? Yeah, this is negative. This is... Wait a minute. This is Wait, this is negative. Oh, thank goodness. Okay, so this is positive 12. Minus 16 is -4. Yeah, that's correct. Okay, so this one worked out. Because this one produces 0 remainder, therefore this is a 0, which means x minus 4 is a factor. Factor of what? Of h of x. So we successfully found 1 factor. This is a bunch of negatives. Because this starts off as cubic and we divide it by x minus 4, therefore this one downticks to squared. So this is a quadratic. I'm going to factor the negative from the quadratic first. And this is just a perfect square trinomial because half of this is 2, 2 squared is 4. So we know this factorizes following algorithm into x plus 2 squared. We will multiply to this one to get the full answer. Fully factored form. Don't forget the negative. There it is. Okay. Let's get to graphing. First 0, we have x is -2. Second 0, we have x is equal to positive 4. Again, we already noted that the parabola, because it's cubic but with a negative coefficient, it starts up and goes down like this. So from this one, oh, this is multiplicity 2. Oh, be careful, be careful. We have a multiplicity of 2 on the x plus 2 factor, which means this is the touch and go. Starting from up, do the old touch and go. It's going to go something like this. Come back down. Follow this end behavior that we already made note of. So like that. So I'm gonna keep sounding like a broken record. Your graph will look something like this. Where does this happen and how long does it go for? I don't know. This is again where it's just artsy fartsy. So something like that, but I don't like the way it looks, so I'm gonna leave it cut off. So I don't commit myself to saying where that turnaround is. And we're good with the graph of h of x. Perfect. Alright, and then next problem up. Do I even want to do this problem? It's kind of annoying. Let me think about this. Shall I just move on? Let me think about how many things I need to do. I would like to do. We have... Maybe this deserves its own separate section, I feel. Yeah, let's keep it short and simple. Let's just move on to the next one. And I'll save the graphing ones for next time. Okay, so next function up we have kind of a further annoyances. We have x power 4. Alright, so here it is. So new function, I'm going to start back up to f of x. New function is 8x4. So that's kind of annoying. This is also kind of annoying. So minus 50x cubed. And then we have plus 69, nice, 69x squared. And then plus 72x. And lastly, minus 135. So that is the function. It is x power 4. Do we have any factoring considerations to make note of? Well, we have 5 terms. This one has no 5s. This one has 5. This one has no 2s. This one has no 2s. So we can't factor something from all 5 terms. Can we factor by grouping? It looks more hassle than it's worth. So I'm just going to jump straight to synthetic division. So we have factors of 35, which will be 1. Again, it's probably unnecessary to list the 135, but some teachers require you to do this for full credit. Is this divisible by 3? Yes, it is. So 3 times 45. Okay. 3 times 45. Alright. So next number up is 5, and then 5 times 27. Next number up is 9. 9 times 15. And I think that's it. Yes, that's all. Those are all the factors of 135. Factor pairs. Factors of 8. We're going to have 1, 2, 4, and 8. Okay, so there are a bit of candidates to try out. The numbers are kind of... they're kind of intermediate. They're kind of smallish / intermediate, but let's do Descartes' rule of sign first. We have positive changing to negative, so that's 1 sign change, 2, 3 sign changes. So we're guaranteed 1 positive real solution. So I'm going to start with my 0 candidate as a positive candidate first. And let us try simply 3. See what happens. You know what, let's try 1. Why not try 1, right? Will 1 work? Probably not. Let's go back to 3, I'm sorry. Yeah. So let's extract the coefficients, making sure all terms are present and accounted for. 4, 3, 2, 1, 0. Perfect. Negative 50. Let's make sure I copy the signs correctly. It's positive 69. Nice. Then we have positive 72. Negative 135. Okay. Let's drop that. Product. Sum. Product. What is that? Negative 75 minus 3 is negative 78. Yeah. Then summate that one. We're going to get negative 9. Product. Negative 27. Sum. Positive. Yes. This looks good. Oh, I think it's good. It's perfect. I know myself too well. Except when I don't. Alright, that's going to be 0. Perfect. So this one produces 0, therefore 3 is a 0. Therefore, x minus 3 is a factor of f of x. So let's write our skeletal progress. F of x is equal to, so far, x minus 3. I'm going to take a quick sip of lemon tea. Almost said honey lemon again. Okay. Checking this real quick. We can do some more factorization. We have one guaranteed positive real solution, which we've just found. We may have two other positive real solutions, but let's check negative solutions real quick. So if we plugged in a negative value into f of x, then this will still be positive. This will become positive. This will become positive. This will be negative, and this will be negative. So we're guaranteed one negative real solution as well. So I'm going to try negative 3. Right, why not? Let's try negative 3. Drop the 8. That is negative 24. That looks bad already. This looks like it's going to be way off. Okay, so I don't think negative 3 is going to work. Let me try negative 1. Negative 34, positive 34, sum is failure. Well, that gets us a positive solution. Alright, so let's make note of that. So negative 1 has failed as a 0 candidate, but negative 1 plugging in will give us a positive solution. So hopefully, if things get worse and worse, we can at least try to use intermediate value theorem. So again, negative 1 did not work. Wait, why didn't it work? Hold on, let me see something real quick. No, I can't. It's lost. Okay, I should have been more careful. That's okay. Let's stick with the let's do negative 1/2. These numbers look kind of nice. Drop the 8. Half of that is negative 4. Negative 30. Half of that is positive 15. Ooh, we're not quite there yet. That one gives us, what does that give us? Positive 6. This gives us negative 3. This gives us positive 42. Positive 42. Alright, so negative 1/2 is not super useful. Also takes us to positive remainder. So let's try something more drastic than negative 1. Let's try negative 3. I don't think negative 3 is going to work, but it might inform us from intermediate value theorem. So let's drop this and multiply. Yeah, I don't like the way this looks already. It's negative 50. Yeah, see that? It's too much. But again, it could be informative. This one gets a big negative value, and then if you summate those, that gives you a big negative value. Which means what? We have negative 3 reporting a negative 3 remainder. Negative 3 gave us a negative remainder. Therefore, there must be between negative 1, according to intermediate value theorem, between negative 1 and negative 3, there must be a 0 between those two, because of the alternate signs in the remainders that they've given us. So what is between negative 3 and negative 1? 3 over 2. Okay, negative 3 over 2. Did we try that? No, we tried negative 1/2. So negative 3 over 2. Hopefully this works. So half of 8 is 4. 4 times 3 is negative 12. Alright, looks okay. And then summate is negative 38. Still okay. Half of 38 is 19. 19 times 3 is 27. Wait. Why can't I do this anymore? Half of 38 is 19. 19 times 3 is just 60 minus 19. 41. Right? Right? What am I saying? You know what? I don't trust my brain anymore. So 19 times 3 is essentially 20 times 3, which gives us 60. But we don't have 23s. We only have 19, so minus 1 3 gives us 57. 57! I don't know, I said 51. 57. Positive 57, of course. Summating those two, we're going to get 48. Yes. That does not look too good. half of 48 with a negative sign is negative 24. Negative 24 times 3 gives us too large of a negative value. Okay, let me double check my math real quick. Hold on. This one should have worked because it's the best one between negative 3 and negative 1. But let me see. Yeah. Okay. Yeah, I think that's whatever. So we're going to get a negative value that's bigger size than 45, so we get a negative remainder. Okay. But worry not, that itself is informative. So we've concluded that negative 3/2 also gives us a negative still. So we narrow the search. Cross out the negative 3. Cross out this one. So between negative 1 and negative 3/2, there must be a 0. According to intermediate value theorem. So what's between negative 3/2 and negative 1? Ugh, that's so annoying. Oh, 5/4. Maybe 5/4, right? Is that between? Oh, my brain. I'm so out of it today. So 5/4 so negative, to further complicate things, in comparison to negative 3/2. This is 6/4. So negative is smaller, and okay, good. Yeah, this should, it's gotta be negative 5/4. It's gotta be. So negative 5/4. All right, here we go. Hopefully this works. So 2 times 5 is 10. So we have a negative 10. Negative 36. Okay, negative 36 is divisible by negative 4. So we get 9. 9 times 5 is 45. Good. Summate that one. We have 4 5s, which is 36. Positive 36, that looks good. Fourth of 36 is 9. 9 times negative 5 is negative 45. Perfect. Okay. Found him. There it is. So we have the second 0, which means the second factor is x plus 5/4. This is a quadratic. We could factor out a 4 from each of those terms. So 4 out of 2x squared minus 9x plus 9. We could take that 4 and distribute it to this factor to beautify it, thereby getting f of x is equal to x minus 3 times 4x plus 5. Is this a factorizable quadratic? Let's use discriminant test real quick. So 9 squared is 81. And then minus 4 times 2 times 9. What is that? 8 times 9 is 72. 72. Oh, it's perfect. Okay, so this one is a factorizable quadratic. Good, 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 good. So factors of 1, factors of 2, 2 and 1, factors of 9 is going to be 3 and 3. We get 6 and 3. Perfect. It's got to be that one. So the 2x has to be multiplied to the 3, and then the 1x has to be multiplied to the other 3. Both signs are the same, both sides are negative. Wait, that's a 3. As stated before. Okay, so that is fully factored form right there. What a lot of work. I guess that's the worst part of this section. If you're given bad quadratics, or I mean, sorry, if you're given bad polynomials, it's kind of a chore. But here we are. This is fully factored form for f of x. So all that work is to just get fully factored form. Now we can start to graph. All right, we have 0 number 1 at negative, what was it? Negative 5/4, which is like here-ish. So 0 number 1. Then we have 0 number 2. Where's that? What's the next smallest one? This one. So at positive 3/2. There-ish. And then we have the same zeros. We have repeated solution right here, and x is equal to positive 3. And because it's going to be x minus 3 squared, we have a quadratic motif happening, a parabola motif happening at this particular 0. So it's going to be something like that. All right. Let's evaluate end behaviors. This is x power 4 with a positive 8 coefficient, so it's going to be going up, up. All right. And let's just make sure things go very smoothly. So this one goes through our first 0 straight down, because again, this is multiplicity 1. So it pierces straight through, turns back around, goes into 0, crosses x-intercept number 2, which is right here, multiplicity 1, so we pierce right through. There's a turnaround, and don't forget, we have a parabolic-like motif happening at x minus 3 squared location, which is happening right here. So we have a parabolic motif like so. And we'll connect those two as smoothly as possible, and that's the graph. So here's one way of looking at it, but I'm going to draw it like this. So we are finished graphing this particular function. Let me double check the end behaviors. This is positive with an even powered exponent, so it goes upwards, upwards, yes. Okay. Very good. And then the last problem of this set. What do we have? We have h of x is equal to 18x power 4 minus 75x cubed plus 8x squared plus 17x and then minus 4. Alright. That is the function. Let's take a quick peek. Can we do any special factorizations that are easy to do? We have 1, 2, 3, 4, 5 terms. Probably not a good candidate for factor by grouping. We can't factor something from all 5 terms because we have odd, we have even. This only has factors of 5 and 3. This has no factors of 5 or 3. So let's just jump straight to synthetic division. Candidates of 4, we have 1, 2, and 4. So not very many, so that's good. Factors of 18, we have 1 times 18, and then we have 2 times 9, and 3 times 6. That's it. Alright, so where do we begin with our first 0 test candidate? Let's do Descartes' rule of sign. We are changing from positive to negative. It's 1 sign change, 2 sign changes, and then 3. So we're guaranteed 1 positive real solution. So let's begin like that. Alright, so we have 4, 3, 2, 1, 0. All terms are present and accounted for. So let's extract the coefficients. 18, negative 75, positive 8, positive 17, and then negative 4. Since I messed up the signs twice already, I'm going to double check to make sure my signs are correct. Okay. Alright, first candidate. The numbers are kind of largish. Kind of. So I'm going to pick positive 2 as a first test. So again, we're guaranteed 1 positive real solutions. So I'm going to pick 2. Since these numbers are fairly intermediate looking. So drop the 18. Times 2. Summate, we get negative, what is that, 39? Yeah. Right? Yeah, that's correct. And then product of that one is going to be negative 80 minus 2 is negative 78. Yes. Yeah, and then summate those two, we get negative 70. That's already looking bad, unfortunately. We get negative 140. But this could be useful, you know? So we have a negative answer. We have a negative situation. We have negative. Okay. So that means 2 is not the proper 0 candidate. It snowballed a little too much in the end. So we're going to pick a smaller value. So 2 as a 0 candidate gives us a remainder of negative-ish. So because it got us a negative value, 2 is not a 0. So let's try 1. I don't think 1's going to work though. But we can maybe narrow down some more possibilities using intermediate value theorem yet again. So positive 18, summate, we get negative something with a 7 to 57. All right. Product is negative 57. Sum is negative 49. Product. Sum. Oh, it's a negative 2. Well, that's not the best. Okay. And unfortunately, neither of those two are very useful, since both of them yielded a negative remainder. The intermediate value theorem can't really help us out. So let us pick something that's smaller. Let's pick 1/2 at this point. Yeah, let's pick 1/2 as a possible 0 candidate. So drop that. Product. Sum. Product. Sum. Oh, this looks bad because we have a fraction. Okay, this is bad. But, you know, same drill. We're going to continue on just to see what the remainder is going to be. So we have negative 12.5. Summate is positive 5-ish. Product is positive. It's positive 2.25. Which means it's a negative result, which is also negative. Okay. That's not very useful either. Let me check the character rule sign again. This is 1 sign change, 2 sign changes, and then 3. Yeah, so we're guaranteed 1 positive one, just not the right one. Wonderful. So it seems that we have to drift to the higher number territory, which is kind of rare. At least for the problems I make. Okay. Or, do we go even smaller number? I wish I should have kept my work, but I've been deleting my synthetic division work just for sake of clearing the visual clutter. Let's try 1/9, since that's the easiest to try right off the bat. All right. Product is 2. Summation is negative 73. That's already bad because it's not divisible by 9. Shall we continue? Let me think about this. You know what? I'm going to continue it just to see the remainder in the end. And hopefully we can use intermediate value theorem, which has been inapplicable so far. So this is approximately negative 72. So it's going to give us like a negative 8.333. Yeah. No. 1/9. I think that's correct, right? So we have negative 1/9. Yeah, negative 1/9 left over. So this is correct. Summating that, we get negative 1/9. And then product that gets us negative 1/81. Well, it's practically 16. Practically 17, and then we multiply that one. It's going to be a it's small. It's a small positive. It's not 36. If it was 36, it would give us 4. But since it's less than 36, it would give us less than 4, which means our answer will be negative yet again, which is not very useful. Okay. So 1/9 has failed. 1/9 also yields a negative remainder. Am I just going out the wrong direction? Shall we go with positive 4 then? I feel like that's going to be way too big. Well, what course do we have? Alright, we have 18, and then we have 8 times 9 is 72. Okay. Negative 3. That does not look too bad, actually. And this one right here. Summation. Oh, it's going to be too big. Yeah. All right, we have 20, 80. Yeah, that's going to be positive answer. But, this is a big positive. This is also big positive, right? We finally have something to go off of for intermediate value theorem. Good. So let us make note that a 4, putting a 4 as a 0 candidate resulted in a positive remainder. So therefore, according to intermediate value theorem, we should be guaranteed a positive 0 between 4 and 2. So the question is, of those, what is between 4 and 2? That doesn't make any sense to me. What number do we have that's between... Huh. I really hope this is not one of those goofy troll problems that I made for myself. No, we're guaranteed one positive real solution because of Descartes' rule of sign. It's plus 1, 2, 3, yeah. We're guaranteed one positive solution. So, what I'm saying is this, because this is exponent 4, there's a chance in some situations where your graph is going to hover above your x-axis and therefore have no x-intercepts, but because Descartes' rule of sign informs us that we have up to 3, we're guaranteed one solution. And I worry that maybe I copied things wrong again, so let me check to make sure all my signs are correct. Yeah, okay. They look like they've been copied correctly. This is positive, negative, positive, positive, and negative, yes. Okay. Again, this is very interesting because according to this one, we're supposed to have a 0 between 4 and 2, but I don't see any numbers between 4 and 2 that we can successfully generate given what we have. So that could mean that I messed up the mathematics somewhere yet again. And that's always a sad situation. Let me check 2 again real quick. So that for sure gives us 36, and hopefully if I do this right, this is a 9, which is 45, so 39, yes, with a negative sign. Multiplying that one, we get negative 35 times 2 is negative 70, 80. What am I saying? What am I saying? Negative 70 plus 8 is 78, yes, negative 78. Summoning those two gives us negative 70. Product, yeah, it's too big. Okay, so that old work was correct. We just get too big of a negative in the end. Interesting. Maybe I messed up the times 4. Maybe that's what's going on. Let me double check again. Yeah. 18 is 2 times 9, so 8 times is 72, yes. So we get negative 3 as a remainder. Then negative 12, summoning that. Negative 4. Wait, what? We have negative 16. 1. Huh. Okay, well, that means I just screwed up the math. That means I messed up on this one. Alright. Wonderful. Absolutely wonderful. Alright, so we have a 0 at for x is equal to 4. Therefore, we have a factor for h of x. We have one factor is x minus 4. Okay, which that is a cubic at this point, so we can continue on with synthetic division. Cross it out. Because the 4 actually got us a 0. Let's try 4 again, because that's a quick mention, hark back to before. If your 0 candidates didn't work before, they're not going to work again. So let me try 4 yet again. Because if it worked once, it might work another time, or it might not work at all. So there's that. Let's multiply that. It probably won't work. Yeah, it's too large at this point. Yeah, okay. So I'm going to stop there. We probably don't have any other real positive solutions. So we can stop with the positive test. Let's do the negative test real quick for Descartes' rule of sign. This one will become positive, this one will become positive, this will still remain positive, this will become negative, and this will remain negative. So we are guaranteed one negative real solution. Okay, that's nice. Since positive 4 worked, why not try negative 4? No, that's not going to work. That's not going to work. Let's try negative 1, see what happens. Multiplication gets us negative 18, that's too big. We need a fraction situation. Yeah. Oh, I should write this down just to be good, just keep good form. And then times this one is positive 21. Summation is 17, right? Yeah. Multiplication is negative 17. Summation is negative overall. So that means that negative 1 has failed as a 0 candidate, but it reported a negative result. So let's keep track of that. So we need something smaller than negative 1. Maybe negative 1/2. Alright, drop the 18. Multiplication is negative 9. Okay, negative 12 summation. That looks kind of good. Half of negative 12 with a negative is positive 6. Summating that is positive 2. That looks good. Negative 1. Perfect. Alright. Thank goodness. Alright, since negative 1/2 works as a 0, that implies that x plus 1/2 is a 0. We can factor out 2 from each of those to put it here. Remember, this is a quadratic. So 9x squared minus 6x plus 1. Take the 2, slam dunk it there to generate a better looking fraction. A better looking factor, I mean. So there it is. Alright. So we still have a little bit left over. We have this remainder of 9x squared minus 6x plus 1 as a quotient. Factors of 9, 3 and 3, 9 and 1. Factors of 1, 1 and 1. We want a 3. We want a 6 in the middle. We can get that by having 2 3's summed together. So that's probably the way we're going to go. So 3x, both signs are the same. They're both negative. Hey, it's a perfect square. Half of this one is 3. 3 squared is 9. Yes. So we have the same factor, so we can just lump them together and just call it 3x minus 1 to the power of 2. And thus we have achieved fully factored form. If I can get this to fit. Okay. I think I can delete some stuff at this point. We don't need the synthetic division work anymore, so that is done. And then we don't need Descartes' rule of signs. We don't need the intermediate value theorem anymore because we already have the fully factored form right here. Cool. Okay, so what do we have at this point? We have a 0 at 1/2. So negative 1/2, I mean. So that's right there. We have a 0 at positive 1/3. That's like here-ish. I don't like how close everything is. And then lastly, we have a 0 at positive 4 right there. Cool. End behaviors. This is a positive coefficient, and it's a even powered exponent, so it's going to be doing the parabolic-like up type of situation. Alright. So from here, we just need to hit, multiplicities, right? We have a multiplicity of 2 on the magenta. So it's parabolic at the magenta location. So it's going to be going like this. We're going to pierce through. And then it's going to loop back around. We're going to go back up. We're going to do the touch and go at the magenta. Again, parabolic nature at the magenta. There it is. You're going to loop back around, crossing through this orange 0. So something like that. Again, this one is going to be doing something like this, probably. This one's like something like that, probably. And that should be it for the graph of h of x. Okay, things got a lot smoother afterwards. Once my brain was warmed up, I guess. Okay, there's something I do need to do in like 30-ish minutes. So I'm going to call it for now. Later on, we're going to cover this type of junk right here. Basically, we're now going in reverse. Instead of starting off with a function and then factorizing it to graph, we're going to start off with the graph, and then we're going to ask ourselves which of these, if any, are in agreement. Which of these, if any, could be a possible function for the graph on the left. Yeah. That's the plan anyway. And as you see, there's a good number to go across. So, you know what? Let me just hover over these. So if you wish to jump ahead, you can just take a look at these problems. And you can save the video for when you want to check your answers. So here is the first two. Here are the second two. Third pair. Fourth pair. And the last one's just a template. Okay. So the directions again are for each scenario, which function, if any, are consistent with the graph to the left. So there could be multiple answers. There could be one answer. There could be no answers. There could be two answers. There could be four answers that are correct. But I think there's like a variation. Some of them are like two answers. Some of them are like no answers. But I don't think there's anywhere all four is consistent with the graph to the left. Okay. Let's not do any sort of saving. That concludes it for now. I'll probably be back later. I know I said that last time, but some things came up. So hopefully I'll be back in maybe several hours, and then we'll go over those graph problems. On that, you have a good one. See you next time.